Today we're going to discuss some basics concerning pH. Naturally, when we're presented with something we don't know nowadays, the first thing we do, Google it. So on this page there are three answers. The first is the definition from Merriam-Webster. The second is from Wikipedia, everybody's go-to choice. And the third is from a website called thought.co. As you can see, all of them are correct. But I have to say the easiest to understand is probably the last one. However, it is also the least specific. So let's go through these definitions. First of all, pH only applies to aqueous solutions. Why is this? Because water has the ability to undergo what's called dissociation. This occurs naturally. The process of water dissociation is seen here in the top, where two water molecules interact with one losing a hydrogen ion or a proton and the other acquiring this hydrogen ion. This produces two charged ions, hydronium and hydroxide. However, oftentimes we like to simplify things, and so the second equation or the second process is sort of the shorthand version, although not entirely accurate, as the one above. In this instance, one water molecule dissociates to produce a hydrogen ion, also known as a proton, and a hydroxide ion. On the bottom, the equation that's outlined is essentially a constant for all aqueous solutions, where the concentration of hydrogen ions multiplied by the concentration of hydroxide ions always equals 10 to the minus 14. So if we go back to our pH definition page, we see that the first two definitions mention that pH is equal to the negative algorithm of the hydrogen ion concentration. So here is the definition of pH written as a mathematical equation. I know there are some of you out there that are going to be thinking, oh my gosh, I'm very intimidated right now. There's a lot of numbers, There's no reason to be. And I'm going to show you why. If you grab your calculator, in this example of pH, the concentration of hydrogen ions we're going to use is 1 times 10 to the minus 5, or 0.00001. So if you enter 0.0001 into your calculator and you hit the log 10 button, what do you get? You get minus 5, But the pH is equal to the negative of the log 10 of hydrogen ion concentration. So simply a negative of a negative is a positive. So the pH of this equation is 5. The pH scale ranges from 0 to 14. Why? Math. Number one. Number two, the equation from their previous page, right? Hydrogen ions constant times hydroxide ions always equals 10 to the minus 14, And so I've worked out the math at the bottom, And again, some of you are thinking, oh my gosh, this is way too many numbers. Well, let's look at it in a graphical format, So the equation's at the top, and here's the graph. The graph, again, the pH scale is 0 to 14, all right? In this table, what I've done is I've taken every pH and I've shown what's the concentration of hydrogen ions versus the concentration of hydroxide ions. If you look at them and you actually do the math on your calculator, you'll notice that in every instance, it always equals minus 14, 10 to the minus 14. So in this, what's another good example about this is when you look at this, it sort of gives you sort of a visual representation of the change of hydrogen ions and hydroxide ion concentration as pH changes. The lower the number, the greater acidity. Why? Because in acids, the concentration of hydrogen ions is more than the concentration of hydroxide ions, where the higher the number, the more basic. Why? If you look at from 8, 9, 10, 11, 12, 13, 14, the number of hydroxide ions is greater than the number of hydrogen ions. At neutral pH, the concentration of hydrogen ions is equal to the concentration of hydroxide ions. So again, If the pH number decreases, goes from 5 to 3, for example, the solution is becoming more acidic. If the pH number increases, okay, going from 8 to 10, the solution is becoming more basic. On the right-hand side, I've listed a few examples, okay, of substances at different pH. In general, acids and bases also taste different, with acids being a little sour, bases being a little bitter. Although I don't recommend you tasting drain cleaner to try this out. Very, very, very dangerous. Changes in pH in living organisms can be very dangerous, since each step in that pH scale is equal to a 10-fold change in ion concentration. Changes in ion concentration can cause damage to proteins, nucleic acids like DNA and RNA, and even lipids. So let's work through a couple of examples. Again, we're going to do the math to see how big these changes are. So the first example, a solution has a pH of 6, it increases to 8. Okay, so the question is, what is the change to the hydrogen ion concentration? At pH 6, the hydrogen ion concentration is 10 to the minus 6, whereas at pH 8, it's 10 to the minus 8. Okay, first let's consider how many steps we're moving, right? 6 to 7, that's 1. 7 to 8, that's another one, that's 2. Okay, each step is worth 10. Okay, so now what do we do? Well, it's 10 times 10. Okay, everybody can multiply 10 times 10, so that's 100. Okay, since we're moving up the scale, okay, the concentration of hydrogen ions is going down, okay, by how much? 100, a 100-fold reduction in hydrogen ion concentration. In this example, the solution also moved from being acidic to basic, okay? Not so hard. Let's try another one. Here we have a solution where the pH decreases from 12 to 8. Again, what's the change in hydrogen ion concentration? Well, at pH 12, hydrogen ion concentration is 10 to the minus 12. At pH 8, hydrogen ion concentration is 10 to the minus 8. How many steps are we moving? Okay. 12 to 11, 1. 11 to 10, 2. 10 to 9, 3. 9 to 8, 4. Okay. So first and foremost, what's the fold change? 10 times 10 times 10 times 10. That's 10,000. So in this instance, we're going from 12 to 8, pH 12 to pH 8. We're going up the scale. The hydrogen ion concentration is increasing. Increasing by how much? 10,000. Additionally, if you look at the pH, this solution is still a base. Not as strong, but nevertheless still basic. Let's look at one more. In this example, the solution's pH increases from 3 to 6. What's the change to the hydrogen ion concentration? Okay, so again, first things first, how many steps? Okay, from 3 to 6, that's 3 steps. Each step is worth 10. 10 times 10 times 10, that's 1,000. Okay, we're going from 3 to 6. We're moving down the scale. So we're becoming more basic. So that means we have a decrease in hydrogen ion concentration. By how much? 1,000-fold. Okay, again, this solution is still acidic. It is pH 6. That's still considered an acid, but it's not as strong as an acid of pH 3. I hope that this video gave you a better understanding of pH. pH can be a little confusing, but with a little work, you can master the subject.